Wait, you actually have a...
Yeah. Hey, Owen, can you hear me? Yeah, go ahead.
No, Michael, you just think comments.
Are you like actually doing this? Was nobody here for Trig identities? Are you just doing the screen?
Yeah, just the screen. Just the screen and my voice. It's funny, it doesn't say that he's actually viewing the thing. He's got? All right. Hey, Owen, welcome.
That's cute.
Yeah.
Oh,
I can't hear Owen, but at least he can hear me.
What's going on?
Owen, I think you can type your questions on the right side of the screen there, if you have any, or fire them to Cam, and we'll go from there. All right, let's get started. It's coming. Oh, it's coming.
How do we get access to that?
I'll show you after. Yeah, so this because Owen's not here, we're gonna he's watching the lesson right now, which means that this will be a video that you can all access after the fact. It goes directly to YouTube when I'm done here, and then if you know how you guys have that Google Apps thing. Yeah, so you'll have access. I'll let you know how you can get access to it. We'll try it when somebody goes to there. Yeah, it's a Google Hangout, but yeah, probably. So. All right, let's get started. We're going to talk about solving trig equations today. When we solve a trig equation, it's not really any different from solving other kinds of equation. We're trying to find the x value that makes the statement true or the equation true. So I'm just going to jump in and start looking at some examples. We'll start with some simple ones and then move to some more challenging ones. So let's solve the following. On the interval 0 to 2 pi. What this means, remember that the trig functions are periodic, which means that there should be an infinite number. If there are solutions, there should be an infinite number of them. So we kind of have to restrict the domain that we're looking on. It's kind of like the Ferris wheel one, where you try to figure out at what time is the Ferris wheel above 50 meters high. Well, if the Ferris wheel keeps going around and around and around, it's going to, be above 50 meters a lot of places. So here I specify that we're only looking for the solutions between 0 and 2 pi. Sometimes the solution might be between 0 and pi. Sometimes it might be from negative 2 pi to 2 pi. So we'll just make sure that any answers we get, we restrict our domain there. Here we go with the first one. So the first one here, 2 sine squared x minus 1 equals 0. We want to find out what value of x is going to make this equal to 0. And some of you might be able to, if you looked at this long enough, I said, here you go, and I gave you enough time, some of you might be able to kind of figure out the answer. We're going to do this kind of algebraically, though. We're going to treat it like we would solve every other equation. So we'll start by adding 1 to both sides to get rid of the 1. Our goal is to get x. In this case, probably on the left is a good spot because it's already there, but our goal is to isolate x. So let's start with adding 1 to both sides. Where do we go from here? Yeah, let's divide both sides by 2. And then here we'll get that sine squared x is equal to 1/2. We're getting closer. Just want to get x on one side of the equation all by itself. Yeah, so that's a good idea. We need to get rid of that squared, so let's square root it. When we square root sine squared, we'll just get sine. And don't forget, when you take the square root, there's always a positive version and a negative version of your answer. So the answer here is plus and minus the square root of a half. No, we have to find x. So we actually have to take this further, and in order to take this further, oh, I can't scroll down on the page. Can I hide this? Sure. In order to find sine x, we need to, in order to find x, we have to get rid of this sign, and we do that with the inverse sine. I'm going to split this into two different parts. There's one part here when sine x equals positive root 1/2, and there's one part when it equals negative root 1/2. Just to make this a little bit easier, the square root of a half is the same as, I'll put a plus and minus out here, is the square root of 1 over the square root of 2. Is that okay? Good question. How about now? What's the square root of 1? And to answer Leslie's question of how is that easier, now this looks like a special triangle scenario, right? So I'm going to split it into two. We know that sine x is equal to positive a half, or sine x equals negative a half. So, sorry, I said half. It's a root 2, isn't it? So we can go to the special triangles. We can look at sine. If sine is here, we're going to have the opposite side as 1, the hypotenuse as root 2. That's a special triangle. The related acute angle here. This is the question that a lot of you had some trouble with on your last test. The related acute angle is going to be pi over 4, but we need to find all the places where sine x is equal to positive 1 over root 2. Well, that happens in the first quadrant, and it also happens in the second quadrant. So in this case, x is going to equal pi over 4, or x is going to equal this angle right here, which is 3 pi over 4. Is that okay? Two solutions, and that's just for the part here where sine x equals 1 over root 2. We haven't even touched the part where sine x equals negative 1 over root 2, but I think you guys see where this is going. Where does sine x equal negative 1 over root 2? Yeah, these quadrants down here. So sine x equals negative 1 over root 2. So we need to know this angle right here. The good thing about this is the related acute angle hasn't changed. The related acute angle is still pi over 4. So in here, we have a pi over 4, and in here we have a pi over 4. So from this section right here, we get that x is equal to pi plus pi over 4, which is 5 pi over 4, and x is equal to 2 pi minus pi over 4, which is 7 pi over 4. One trig equation gave us 4 possible answers. Any questions about that? Let's try another one. Yeah, I'll wait. No, that's a good question. Yeah, Brendan said they're not all going to be angles from those special triangles, and no, they're not. So we're going to do one next where they're not values. But if they are values from those special triangles, I want you to be able to recognize that and then give me exact values for your solutions. John? And 5 pi over 4 and 7 pi over 4. 4 different answers here for the one solution. And you can check, just like in grade 9 when I give you an equation, 2x plus 5, 2x equals 10, you come up with an answer of 5. You can plug your answer back into the equation and see if you get the left side and the right side are the same. That still works here. So if you're not sure, somehow you thought maybe you messed up on the 5 pi over 4 and the 7 pi over 4, plug it into the equation and see what you get. If you get that the left side is equal to 0, which is the right side, then you're all set. Guys ready for the second one? No, okay. Just wait. Should tell some jokes or something. Boom. I think they call that clubbing, right? They call that clubbing. I'm not sure. Oh, really? Oh. All right, let's have a look at part B. Okay, sorry, I can wait. Sorry, I'm not trying to rush you. I just thought you guys were ready. I'll wait. Really slow at reading my writing. Is that what you're saying? All set? All right, let's move on to the next one here. This one maybe looks, I don't know, easier, harder. I think it probably looks easier. There's no squared in it. There's just the two terms. We could make it sine over cos, but we don't have to. I would say let's start by adding 5 to both sides. No, it's going to be short. We're almost done. Just like in the last one, we had to do a lot of rearranging first. We've kind of done the rearranging. We now have that tan x equals 5. How do we solve for x? Take the inverse tan. Don't forget tan is positive here and here. Our calculator is going to give us the related acute angle. You guys try that on your calculator and see what you get. We'll go 2. Radians?
I got 150.
So the 1.37 radians was this angle right in here. We also need this one here. So yeah, it's pi more than that. So pi plus 1.37. Let's see if we can do this. No, I can't do this in my head. I think that's going to be a 5, and this will be a 4.54. Somebody check that. 5.1. I knew I was going to mess something up there. That's an example right there, just like Brendan was asking earlier. Are they all special triangles? No, they're not all special triangles, and this is an example of one that's not a special triangle. No, that's a really good question. So Tiffany just asked, because this wasn't a special triangle, is that why we didn't get 2 answers? Sorry, 4 answers. The reason why we got 4 answers over here is that this was a sine squared. The sine squared meant when we took the square root right over here, we got a plus and a minus version. Each one of these trig equations located somewhere, right here, each one of these has 2 solutions. Sine x equals 1 over root 2 in 2 places, and sine x equals negative 1 over root 2 in 2 places. So that's why we ended up with 2 solutions. It was because we had to take the square root over here. So anytime you see a sine squared or a cos squared, that probably means you're going to end up with multiple solutions. I should mention too, I don't know if I have an example for it, like it. I probably do, but remember that what we're doing basically is we're finding when, in this case, it was sine x. When does sine x equal 1 over root 2? Well, that happened here and it happened here. If we This is on the interval from 0 to 2 pi. If we compress this graph so that one full cycle only takes pi radians, and I'm still looking for the solutions from 0 to 2 pi, suddenly I'm looking for 4 solutions instead of just 2 solutions. How does that compression on the graph show up in the equation? If I were to, how does this equation here look different from this one over here? What's that? Yeah, how do you get those more bumps? What changed here to here if this is still 2 pi? We get a compression, right? It's a horizontal compression. And what changes in the equation when you have a horizontal compression? The k value, that value in front of the x. So if there were a 2 in here, that's an indication that you're going to get a compression, which means that your period now is half as long as it was. So if there should have been 2 solutions, but we've stretched the period out twice as much, now we're going to have 4 solutions. That's one thing that often trips students up. So just be aware of that period change. You know, I like to sketch it out every once in a while, just like I did here with the 2 pi, saying, hey, there's 2 solutions here. But wait a second, if we're going to compress this thing, there could be 4 solutions, just like there are up in here. Is that okay? Everybody feeling okay with this so far? Say that again? Well, it's not really, but if it were, then we would have to change this. This would have to be the 2 compression. Yeah, so if it's squared and has the compression, you can have a lot of solutions, right? We had 4 solutions, but it had a compression. We could have, actually this is the graph for this one. We could have up to 8 solutions. Ooh, that's a lot. The compression is because of the k value right in here, this 2. Why is it 4 answer when they're squared? That's a really good question. When there's a square, this is a quadratic equation, right? Because it has a square value in it. When you solve quadratic equations, you always get, not always, you often get 2 answers. You know, you factor it, you get your 2 factors, and you set each factor equal to 0. So the squaring gives us 2 of the answers, which is why when we take the square root, we get 2 answers. The other reason why we get more than 2 answers is that there are 2 values where sine is equal to positive 1 over root 2, and there are 2 values where sine equals negative 1 over root 2. It was just an example to show this. So I think I see where the confusion is coming from. This graph shows this. We manipulated this equation right here down this far to say, right here, down this far to say that sine x is 1 over root 2. This statement right down here is equivalent to what we started with. So what I was getting at earlier, Emily, is I was saying if the graph were compressed, well, we get a compression if we put a 2 in here. So if this was a 2, then we have to kind of worry about how that's going to change things, and it changes things by compressing the whole graph. There are some like this, I think, in the homework. Probably I'll take one up tomorrow so that you can see if we don't get to it today. The square doesn't act as a k value. This acts as a k value. It's actually not. This green 2 in here would give us this graph right here. It's just like a different question. It would be a different question. Let's maybe get rid of it and then alleviate the confusion. Yeah, I might save it for tomorrow. We'll see how we're doing for time, because I do want to give you some time to work. So today we're going to do these, and then you'll have some equations to solve. And then tomorrow it's just you guys solving equations. But we will do one. If it's not today, it'll be tomorrow. All right, let me see if I can find another one of these for you. So far, the examples that we've looked at have been fairly straightforward in that you just kind of move stuff around. We'll do one example now where that's not the case. There are lots of ways that we could do these questions. Some of you might see some connection between what you have here and some of the other stuff. Hey. Which graph? This one?
No, the one.
This one?
No.
Yeah, you can. I was going to get into that a little bit later. But. Guys okay? Let me know when you're ready to go, Emily. You're good? Okay, one of the things that you might notice here, and Brendan kind of said, hey, can we use the trig identities here? And yeah, so Brendan recognized that this right here is one of those double angle formulas. How do you remember it? Practice. You know, it's that stuff that's on page 416, and if you're doing all the questions over and over again, you start to recognize this. So it really is all about the practice, which is why I gave you 2 days to work on those identities, because you really have to do them. The one thing that you'll notice here is that the angle here was just a single theta, and here it's a 2 theta. That creates some problems, right? So we want to make sure that what we call the argument, the thing going into the function, is the same in both cases. So we can do that easily here by replacing 2 sine theta cos theta with a sine 2 theta. Did I do that right? So this question really is saying, hey, where is sine of 2 theta going to equal the cos of 2 theta? Yeah, so Emmy's on the ball today. Yeah, so all of this right here becomes this right here. And then if we divide both sides by the cos of 2 theta, we'll have a 1 on the right and a tan 2 theta on the left. Oh, here's one of those ones with the compression. This is perfect because it's almost like I planned this or something. Two things are happening. One, it's a compression, but it's also working with tan. What's the period of tan? Pi. So when we compress it, we're going to get sort of a full cycle in pi over 2. And then we want the answers from 0 to 2 pi. I needed some way to get all of the cos and sine functions on one side of the equation, and we'll see some of this in a bit. You're right. I could have said, hey, let's subtract cos 2 theta from both sides. I wasn't seeing where that was going to go. You know, I guess I saw that as being, well, then we would kind of work backwards to this and see what we could replace cos 2 theta with, which is okay, and then we would get to a trigonometric quadratic equation, which we're going to do next. But anyway, I thought this might be the easiest way. Yep. No, because remember that the angle here isn't, when you do the division, the angle's not going to change. You know, if this is 45 degrees, the sine of 45 divided by the cos of 45 is just going to be tan of 45. Yeah, we could subtract 1, or we could do that. I wonder if that's going to work out faster than... I was going to say, hey, why don't we do this? No? Okay. Here's what I was thinking. is that we have this situation here where this is happening. Let's just for a minute, I'm going to say let x equal 2 theta. And the reason why I'm going to do that is that we'll come back to this, but I think if I do that, you guys probably know how to solve this. Right. So I just said, hey, this is a little bit complicated in here, but if we just had the tan of one thing equals tan of x equals 1, I think most of you could probably find a way to solve this. And then we'll just kind of backtrack later and deal with this after to find theta. 1 to me looks like that special triangle, this one. Does that work? Tan here would be opposite over adjacent, 1 over 1, so the angle has to be this pi over 4. So that to me says that x is equal to pi over 4. Where else is tan positive? Down here? Which is going to be, what's that, 5 pi over 4? We just found where tan theta equals 1. We really want the tan 2 theta. So this is where that compression comes in that we talked about. This 2 is a compression. We're going to shrink the period. So I'm going to take this and said, hey, if x is equal to 2 theta, that means that 2 theta has to equal pi over 4. And 2 theta has to equal whatever this is, 5 pi over 4, I guess. And now we can solve for theta. That's a really important step. If you have any questions, please make sure you kind of share them because this would be a good time. We are just dividing by 2. That's not the hard part, I don't think, Leslie. I think the hard part is realizing that we just plugged back into here to find x. You had that x was 2 theta. We figured out what x was. Now let's figure out what theta is from this equation back here. Solve this for theta. Theta is equal to pi over 8. And theta is equal to 5 pi over 8. So we took the tan graph, which looked like this originally. Actually, you know what? Forget the original. We don't really need the original. This is our compressed graph. It finished at pi. We said that tan was equal to 1 here at pi over 8. At 5 pi over 8. And then the question originally asked for answers from 0 to 2 pi. We gave all of the answers from 0 to pi. How do we find the other answers? Because we know this is just going to keep going like this. Whoops, I drew that on the wrong side. This one should go like this. Add what? Somebody said it. Why? Yeah, so the other answer that's here at pi over 8 is going to be, well, not 1. I guess technically it is 1 period away. That's how we got this one. But then we can add pi either to here, add pi to here, or we can add 2 pi to here. So 2 pi to here. If we add 2 pi onto each of these, we'll get to the next answer. Or you just keep adding pi, right? So either one of those options. So our other answer will be theta equals this right here, 5 pi over 8. I was just going to add something in here. I was going to add, but I'm trying to think if it's pi or pi over 2. How come you said pi? The period is pi, but now the period is shrunk, so the period is pi over 2. Which is why this worked out. So we can take 5 pi over 8 and add pi over 2. Find a common denominator. So that's 5 plus 4 is 9 pi over 8. And then then we can do it again. Take that answer and add another pi over 2. And just to double check to make sure you did this right, 13 divided by 8 is less than 2, so we haven't gone beyond the 2 pi. So again, 4 different answers here, but these four answers were a result of compressing the graph rather than, yeah. Right. Yep. Yep. Graph it, or if you understand, a lot of you will be able to look at this and say, oh, I just need to add whatever. If you can do that, that's fine. But if you need the visual, draw the picture and see where the next one is going to happen. This picture right here, what part don't you understand? Do you understand this? The tan graph here that was compressed. It was compressed so it finishes at pi. So here's what would normally be a 2 pi version of the graph to here, but it's compressed by a factor of 2 because of the 2 in the original question. This 2 right here.
What is the graph supposed to look like? Because that's really.
This is the graph. This is the graph. In green is the graph of tan equals 2 theta. So the green is tan equals 2 theta. And then this point right here is where the answer was. The solution happened at pi over 8, right in here. And it happened at 5 pi over 8. We then need to find the other ones. We haven't gone to 2 pi yet. The question asked us to go to 2 pi. We should really extend this graph all the way out to 2 pi and know that there's another one solution over here and another one even further out here. The period of this graph is pi over 2, because the period of tan is usually pi, and then we compressed it by a factor of 2, so the period is pi over 2. Well, that's a good question. Our final answer, our last one is at 13 pi over 8. This would be 16 pi over 8. Our last answer is somewhere in here. We can't go much further than that. Really good question. Yeah, if the question just said to give the answers, for one cycle, these pi over 8 and 5 pi over 8 are the answers for one cycle. Yeah. Right. Yeah. Right. The period of our function, this tan function repeats every pi over 2. From here to here is pi over 2. And so that's why we add the pi over 2 in, because that's the period. With a periodic function, every time you add the period, you get to the same place that you started at. Yeah. Is that okay? No. Nice. That's what I like to hear. Now that you've got the basics, let's move on to the hard ones. Yeah. Yeah, for sure.
The regular period for a tan function is what?
Pi. Right. You get half at the. We have 2 options at this point. I can stop and let you do some work and then do some examples again tomorrow, the harder ones. Maybe that would be a better idea. Okay, let's do that instead of me doing all the examples in one day. Yeah, we'll do I have a few, I think 3 different ones to try tomorrow. So here's the work that I want you to try for today. It's on page 426. Question numbers 1 to 3, 5, 6, and then 8 to 10. Give those a try and see what's going on. I think we'll say goodbye to Owen. he's still there. Is he playing baseball? No, I just kidding. But I'll leave Owen on the screen, so if he has questions, we can see his question. No, it's okay.
What is this?
Because it's watching to the screen.
It's sharing my screen, but I'm gonna stop the sharing of the screen. So Owen, if you have any questions, just pop them in the right-hand side of the screen there, and I'll see them eventually. But I'm gonna turn the microphone off. I can't hear him. No. As soon as